The next speaker is Rommel Carvalho from George Mason University. I think Mike gave him a good introduction of what he wants to talk about, which is modeling a probabilistic ontology for maritime domain awareness. And, well,
let me just get set here.
Ontologies are something we should talk about, and there we go.
Well, again, good afternoon. My name is Rommel Carvalho. I'm from George Mason University. I'm going to be talking about modeling and probabilistic ontology for maritime domain awareness. And I just want to acknowledge this was actually a model we used on, funded by ONR project. And I also used this for my PhD work as one of the use cases that I used to evaluate some methodology that I proposed. And also, thank them for funding my PhD. So the agenda is going to be, I'm first going to talk about the objective of this project and why we're trying to use this probabilistic ontology. And then I'm going to actually talk a little bit about what's an ontology and what's the difference between an ontology and probabilistic ontology in our point of view and what we want to do with it. And then, of course, I'll go and describe a little bit of the methodology we use to develop this model. And I don't have enough time to cover everything that we have on the paper, all the rules and the requirements we have in there for that ontology. However, I do want to talk about a few of the things that we saw when we tried to evolve the model. So as we did different iterations and you add new requirements and what happens to the implementation of your model. So I'm going to talk a little bit about that. And then just a little bit about testing. This is actually from another paper. It was presented yesterday by Paulo Costa. And I just want to show that we did some testing and we got some results for that model and talk about some conclusions. So the objective. So the idea was to develop this probabilistic ontology to provide situational awareness. So you have all these masses of evidence, everybody talks about this. You have all this different information you want to put together and you want to connect the dots, but how you do that. And here, the evidence we're talking about could be from sensors or reports from human beings. Although we wave our hands on some things like, if it's from a human being, we assume that it's already structured some way that the system is going to understand that as a point of data. So we're not going to talk about that, a specific problem. So it's part of the Prognos project. The Prognos is a probabilistic ontology and net-centric operation systems. We have published a few papers on the past few years on this project, and I won't go into the detail about it. But basically, we're trying to do high-level fusion using probabilistic ontologies to provide situational awareness. So we're going to use things like probabilistic web ontology language, which is a language that leverages the OWL language in order to provide the definition of uncertainty relationships, which is based on multi-entity Bayesian network, which is a logic that allows you to put together logic and uncertainty. Again, we're talking about high-level fusion here, and we use UNB-Bayes, which is an open-source tool that allows you to develop these probabilistic ontologies and reason with them. So, just a brief introduction. And you have many definitions of ontologies out there. I just want to, briefly describe what I'm assuming they are for our purpose here. And it's, formal representation of some domain of application you're trying to convey. And this means that you're going to have things like types of entities, which we also call classes. So you're going to have person, organization, ship. And you're going to have attributes for those things. So you're going to have a person has a first name or last name. A ship has some ID associated to it. You're going to have some relationships. So a person is the mother of another person. A person is owner of a ship. Your organization is owner of a ship, or some other relationship between those classes. And you're also going to try to represent processes and events like transporting cargo and fishing and other things like that. So that's what you do in your ontology. A standard language out there the communities have been using a lot on the semantic web is called web ontology language, OWL. I know some people have their problems with that. They prefer other things, but it's a standard and a lot of people are using it. So it was developed by the W3C and it's a language to represent ontologies for the semantic web. It was accepted as a standard back in 2004, and the second version now in 2010 is also already available. So a standard tool to model these ontologies is Protégé, and Protégé has this idea that you can develop the things that I talked about before, the types, it's right here. You have maritime transport, where it's the ship we're talking about, and you have organization, person, and down here you have properties and relationship between those classes. And here you can have some definitions. So for instance, we can say that a ship of interest is equivalent to a ship which has a suspicious behavior. So that sounds good. This is a crispy definition for our purpose here of identifying what's a ship of interest. The problem is, and then you could do some inference. So if you have some instance out there on your knowledge base and you know it's a ship, and you know it has some suspicious behavior, then you can classify it as a ship of interest. Well, the problem is that you really don't know if it has a suspicious behavior or not. That's actually what you're trying to find out. And that's where uncertainty plays a key role, because you want to use evidence you have available in order to say, okay, this guy seems like he's a suspicious, but you can't really say that he's doing something wrong. So you can't really say that he has an aggressive behavior or erratic behavior. You can say that it seems like it, right? So that's what we're trying to do. So what's the goal here? No, before I talk about that, sorry. Let's just introduce the probabilistic ontology part. So probabilistic ontology is pretty much the same thing we talked about before. So you have all these classes, these properties, relationships, and you're defining this processing events. But now you're also talking about uncertainty associated to those terms. And now what you're trying to do is actually be able to say something like the probability that this ship has evasive behavior, given this other information, is 50%, 70%, 90%, or whatever you want to define, right? So that's what we're trying to do. Well, how do you do that? So the same way you have Protege as a standard tool to developing ontologies for using OWL, you have UNB-based as a standard tool to develop probabilistic ontologies in PROW. Okay, so I'm not going to go into detail too much about what these things mean, how to create this model and all that. I just want you to capture the idea here. Basically what we're saying, and you can think of this as a Bayesian network. So you have random variables, and they, condition dependent of others, and this is going to be more likely given that, and so on. So basically, what I want to say here is that if your ship has evasive behavior, it's more likely he's not going to be responsive to radio contact, or he's not going to have a responsive AIS and things like that. So this is a simplified, just a fragment of the whole knowledge base we have, and I'm going to talk about a few of those later on. But here I just want you to have this idea that this actually applies to all instances of a class called ship. So as long as you have a ship, which is defined by this guy here, so as long as you have a variable called ship, then if it has evasive behavior, it's more likely that it's not going to be responsive and so on. So that's kind of the difference between the Bayesian network and this knowledge here, this logic we call MIBN. So you can actually instantiate that. So what's the goal here? What do we want to do with this probabilistic ontology? So basically, I showed you a piece of the ontology you're going to have, and a piece of the probabilistic reasoning you're going to have there. So if this happens, this is more likely to happen. And what I really want to do is, use the information you have available for that ontology. So let's say you have some instance called ship 1. Ship 1 is a merchant vessel, and it's not responsive, does not have a responsive AIS, or does not have a responsive radio in the specific snapshot, time frame we're talking about. And then what I want to do is to instantiate those relationships, those knowledge representation here, and actually be able to talk about uncertainty and say, okay, so given the information you have available in your knowledge base and the question you're asking, I can tell you that this ship 1 actually has a probability of 51% of being having an evasive behavior. So that's the kind of thing we're trying to do. That's what we're trying to achieve here. The big problem, the big question here is, how do you do that? How do you come up with this model? So I just showed you a really simplified version of it, just one fragment of knowledge. But as you gather more and more rules and more information, how do you put all that together? And actually, I presented the first iteration of this model last year at Fusion Conference. And I got a lot of questions about, okay, that sounds really good. I want to apply to this other scenario, but how did you come up with that model? And not only on Fusion Conference, but I actually got emails from people from Australia, New Zealand, and Europe, all over, asking me, okay, tell me the secret. How do you do that? How do you come up with that model? And that's actually something that I had to ask myself too. What's the process I have to go through in order to create this ontology? It's not an easy thing to do. So basically, I decided to add that to my PhD work, and let's define a methodology to do that, and that's what I call the uncertainty modeling process for semantic technologies. And on the paper, you're going to see semantic web, but I decided to change it to semantic knowledge because it's broader than that. It's not just for the web. So basically what we're trying to do, this methodology is based on unified process. So this figure is not mine. This is well known for somebody that understand, have seen unified process before. It's out there. So basically what I'm trying to say, you have different disciplines, and I'm just covering a few of them, which are requirements, analysis, design, implementation, and test. And basically what he's saying is you have different phases during your modeling process. In the beginning you have the inception, then you're gonna elaborate on that, do the construction, then the transition. And basically you have different workload. You're gonna do more work on requirements on the beginning of the process, and less implementation. But as you go along on this time step, this process, during the construction, you actually hopefully do less requirement work and more implementation. So that's what happens. But I want to focus in just one iteration, and what happens there, and this is really my contribution, is what you have to do in order in each of those iterations, what you have to do in each of those cycles. So what I'm trying to look at, and this is really similar if you've seen the presentation from the plenary yesterday morning. She talked about Dr. Ansley. She talked about projection and comprehension and data. And this is pretty similar to this top-down approach that I'm having here, which I talk about goals, queries, and evidence. So basically what you're trying to do is, what do you want to achieve? What do you want to ask your model? What are you trying your model to give you information about? So that's your ultimate goal. So I'm trying to identify whether a ship is a ship of interest. So okay, that's fine. But how is my model going to be able to do that? I don't know. Just with that information, I'm not going to be able to do anything, at least not automatically. So you might want to ask your model some questions. So I want my model to be able to answer me does the ship have a terrorist crew member associated to it? And okay, that sounds good. Now you're narrowing it down. But which data do I need to use? Which evidence do I need to use in order to answer that question? Does the model need to use? So you're going to tell your model, okay, you have to see if he's related to any other terrorist, or if he's a member of some terrorist organization. And you can go on and on about different data you could use in order to provide evidence to support that hypothesis you're trying to test. Once you do that, you collect your requirements, then you're going to look at that requirement and see, okay, what do I have here? What are the keywords? And that's basically building your first initial iterations for your ontology. So I'm talking about ships. I'm talking about a person. I'm talking about a person, a ship having a crew member, which is a person. I'm talking about an organization, a member of an organization, and so on. So you build this keyword thing that is building your ontology. And then you have to think about the rules. So some are deterministic, but I'm focusing more on the stochastic parts and the probabilistic part. So you're going to have rules like, how do you use this evidence to answer this question? So you're going to look at this and say, okay, if a crew member is related to a terrorist, then it's more likely he is also a terrorist. So you're going to create all these rules that connect the evidence to how you're going to answer that question, how your model going to be able to answer that question. And of course, later on, you have to put all that information together in order to make your life easier when you actually have to implement that. Up to this point here, we have requirements and analysis design in here. It's all independent of which language you're using. But once you have to implement it, then you have to, okay, which language, which logic I'm going to use. In this case, we're talking about probabilistic ontology language. So, I'm talking about these random variables, having these arrows and relationships and so on. So once you create that structure based on these rules, you can actually talk about the parameters and say what's the probability, the conditional probability that this is going to happen given that other information. And you can use subject matter experts here, which we did in most of the cases. But we also did some research. So we used statistics available in open source papers and books and things like that to define these conditional probabilities. And then once you have all that, you can actually create the scenarios and verify if you covered all the requirements and test it and so on. Okay, so that's the process for one cycle. But what happens when you actually have to evolve your model? Because it's not just one cycle. You don't do it all at once. You actually have to build upon that. So this model is actually incremental. This methodology is incremental and iterative. So I'm just going to talk about a few of the things that changed and how you address that. I don't have time to cover everything. So you know what? Assumptions change. So in the beginning, we called a ship of interest a ship that if and only if it has a terrorist crew member associated to it. I was like, that sounds good for the first iteration we had, for the rules we had, but now we're talking about something different. Now you want to say that a ship of interest is actually a ship of interest only if it's associated or it's part of some terrorist plan. So now we have this idea of terrorist plan and what are the terrorist plan we have involved in there. And also requirements change. So on the first iteration, we had some ideas of trying to identify electronic countermeasure when people use that and so on. But then on the second iteration, we talked with the subject matter experts, and they're like, you know what, for the ships that we're looking at, for the scenarios we're addressing, they really don't have the capability to use electronic countermeasures. So why do we care? Let's just remove that requirement because it's not going to use it anyway. So, things change. And of course, we add new requirements also. So now we're asking things like, is the ship being used as to exchange illicit cargo? Is the ship being used as a suicide ship to bomb a port? And other things on that matter. So basically, during analysis and design, we initially have this model, which is like a lightweight ontology, using UML to represent a lightweight ontology for our model. And you have things like behavior, you have evasive behavior, and normal behavior, and you have the ship here with really just one attribute. But now, in the second iteration, we are expanding on that model. So now we're talking about aggressive behavior, erratic behavior, and now we're trying to differentiate the types of ships we have. So we now have merchant ship, a fishing ship, and navy ship, and so on. And now we're talking about the plan. But hopefully, these changes are incremental. You don't really have to start over from scratch. The other thing I wanted to point out here really quick is that the third iteration, the goal was to go deeper on identifying whether a particular crew member is a terrorist and how we go about that. So we did some research, and this was mostly done by our subject matter expert. He did a lot of research on that, Richard Harbin, who is the second author here on this paper. So we had this idea that the crew member is associated to terrorist organizations, so he's more likely to be a terrorist, or if he's associated to a terrorist person, he's more likely to be a terrorist too. But now we're looking at more things. For instance, what's his background history? How does that influence his idea of becoming a terrorist person? Does he use a communications media frequently used by terrorists on the specific region we're looking at? Is the crew member a potential terrorist recruit? And this is expanding on these ideas here. So you're looking at friends and related people and so on. And is he participating in one of the 4 cliques we have available? And this is introduced by Sageman on that area of interest that we're looking at. So you have different ways to represent that. But my question was, okay, what's going to be the impact of this third iteration in our model? What's going to be the impact in the implementation we have so far? And basically, to our surprise, creating all these new rules and even changing some of the things that we had before, just had to actually change one specific place in our knowledge of representation. So we had this idea that if a person is related to any terrorist, then he's more likely to be a terrorist. Now this was oversimplified, so now we're removing that and actually creating another fragment of knowledge like this one to represent a more complex relationship. So basically what we did is have to remove that and redo the probability distribution for this node. We had the prior probability distribution for that already. So basically for the other requirements I talked about, I added this other knowledge, fragments knowledge here, and with these uncertainty probability relationships. And I reused some of the nodes that I had defined previously, but I really didn't have to make any major changes besides that one that I just explained to you. So here I'm just going to briefly talk about that because it's based on another paper that we presented. And this paper just points to that paper, basically. And we did some manual and some automatic evaluation. And based on the manual evaluation, we did 20 different scenarios. We had the subject matter experts evaluate it, and they said that, this result seems reasonable. And besides that, we did some automatic case-based evaluation where we generate some ground truth, then we sample from that ground truth some reports, and we use that reports to do inference. And then we put some threshold and compute the confusion matrix. And the true positive was like 89%, and true negative was 98%. So we got some decent results for what we had. Of course, the simulation is kind of biased because we're assuming the same things on the simulation as we do when we're trying to model. But it's better than having nothing to test. Finally, conclusions. I showed how to use this methodology in order to create this probabilistic ontology to all situational awareness. I showed how this model evolves, how changes impact implementation and so on. The advantage of this modularity of this logic, which allows you to add new knowledge without having to really change what you had previously done. Did some testing and showed that we got some decent results. And for future work, we do have to work more on scalability and learning features, which we have not done much on that, but we did some stuff on hypothesis management to try to cope with, the growth of the information available. And thank you. That's it. Yeah.
I'd like to learn, and thanks for it. First, I'd like to learn if when the intelligent analysis thing comes into place, like the ontology gets complicated and complicated. Like it's like not just a one ship and one conditional probability. It's like maybe hundreds of conditional probabilities all related to each other and things. But can you compute these probabilities, or can you have some numerical values for a really complicated ontology or a really complicated domain awareness situation?
Well, I think the beauty here is that you really just have to focus on the information. This comes from Bayesian Network, right? You just have to look at that distribution for that random variable given the parents. So it's kind of, you don't have to worry too much about eliciting given all these other information you're going to have on your knowledge. So that gives you, an easier way to actually elicit the probabilities for those. But like I said, you could use some statistics in order to do that, and you could, use subject matter expert, but you could also use learning. However, there is this question of you're putting all these different rules there, right? And some are taken from this expert, and these are from another agency, this other expert. And when you put all that together, you really get a consistent result in the end, putting all those rules, kind of tied together. And that's a question that we have to look into, by doing evaluation, those kind of things, to actually realize if we're actually getting good results.
It seems like the combination of probabilistic ontologies and that sort of iterative approach to revising your goals and revising your assertions might have a good potential for dealing with that kind of common problem with ontologies of data getting stale.
Mm-hmm.
Have you given any thought to how that iterative approach can tie into, which data do we want to keep forever, which data is less useful an hour later or a month later?
Well, that's a good point. I mean, that sure would be useful, but we haven't done really much on that. But it's something we would be willing to look at. It's a really interesting point. Anyone else? One more.
Yes, you mentioned that you have some problem in scalability, which are probably related to the updating of the Bayesian network you have. It's just a guess, but there is this idea of object-oriented Bayesian networks, which are standard Bayesian networks with some fragments which are always the same. So you have, so maybe this can fit to your situation.
Yeah.
And in this case, you can exploit at the moment of the inference.
Actually, I didn't have enough time to cover this, but the MIBN logic I'm using here is actually more expressive than OOBN. And we also, ENB-based, we have implementation of OOBN, and we did some comparisons study with that. The beauty of MIBN is that you actually instantiate the Bayesian network on the fly. So it's similar to OOBN, but it's more automated. And basically, you don't have to look at all the data available in order to instantiate that Bayesian network, because most of them are going to be disseparated of the query given the evidence you have available. The idea is how do you filter the knowledge base you have and just look at the information that might matter to then do the pruning and all that. And that's basically what we're trying to do with the scalability problem.
We have one last question.
Yeah. Yesterday afternoon there was a session here titled Information Fusion with Imprecise Probabilities. And that deals with the issue that you have, which is that it's nearly impossible to agree on a precise number, 51% probability.
Yeah.
So that's
Yeah.
Question I was going to ask.
Yeah, so at this suggestion, you might want to look at higher ways of representing this higher order of uncertainty. And there's this whole field of it which gives you a much more robust solution than the kind of thing you're dealing with, just forcing first-order probabilities into the system.
Just to concern this point, Fabio Kozman did something about probabilistic logic with imprecise probabilities, and there is a natural mapping to an extension of Bayesian networks with imprecise probability, which is called the Cradle network.
He was actually one of the committee members on my PhD work, so yeah.
Okay,
with that.
that's it. We ran out of time. We can ask more questions at the end. Me too.
Thank you.